Today we are going to be talking about logarithm properties and the graphs of log functions. So first of all, let's talk about basics of logs. It is crucial that you know that logs and exponentials are inverses of each other if their bases are the same. 2 to the x, 2 is the base. Log base 2 of x, the base is 2. They have the same base, they are inverses of each other. Okay? If two functions are inverses of each other, they must be symmetric to each other with respect to the line y is equal to x. They are a reflection of each other over that 45-degree line through the plane. Alright, also, if two functions are inverses of each other, their composition must yield back whatever is right here. They undo. F of g of x, whatever that x is, gives you back x. So f of g of 2 is 2. F of g of 3 is 3. Same thing with g of f of x. It must also give you back x if they are inverses of each other. And that's true for any inverses, not just logs and exponentials. If the point 0, 1 is on f, then the point 1, 0 must be on its inverse. If the point 1, 2 is on f, then the point 2, 1 must be on the inverse. If the x-axis is a horizontal asymptote of f, then the y-axis must be a vertical asymptote of the graph of y is equal to g of x. So I say that because that's true. These are all true. Alright, before we go and graph, let's just think about some values of logs. So if we have log base 3 of 27, this is the exponent on 3 that makes the value 27. So you're asking yourself, 3 to what power is 27? Well, 3 cubed is 27, so that value of that log is 3. 5 to what power is 25? 2. 5 squared is 25. 4 to what power is 1? Well, 4 to the 0 power is 1. 10 to what power is 10,000? 4. 10 to the 4th is 10,000. 2 to what power? 2 to what power is 1 over 32? Well, it has to be negative. And then it's going to be 2 to the 5th would be 32, so this is negative 5. For a log, if your argument is less than 1, then the value of your log is negative. If your argument is bigger than 1, then the value of your log is positive. If your argument is equal to 1, while I'm on that, if your argument is equal to 1, the value of your log is 0. So this last one here, 3 to what power? 3 to what power is 1 over 81? Well, it has to be negative, and that would be the 4th power. 3 to the 4th is 81. Okay, let's graph a few logs with some transformations. Okay, log base 2 of x. Okay, first of all, x, your argument can never be 0. Wherever your argument is 0, you have a vertical asymptote. So we have an asymptote of the y-axis. It's where x is equal to 0. So I'm going to draw my asymptote on the y-axis. And now let's get a few values. I'm going to make up a little xy chart. I know the argument cannot be 0. There is no exponent on 2 that would make the argument a 0. So let's start with 1. Log 2 to what power is 1? Well, 2 to the 0 power is 1. So 1, 0 is on the graph. What about when x is 2? What exponent do you raise to get 2? 2 to what power is 2? That would be a 1. So 2, 1 is on the graph. The next nice number would be a 4. 2 to what power is 4? Well, 2 squared is 4. The next nice number would be an 8. Let me go graph this. 4, 2. 2 to what power is 8? 3. So know that these logs are directly related to exponents. They are inverses of each other. So I'm going to go ahead and sketch this now. Just like that. If I were to graph the curve, pretend that went through. Oh, I got off on that. Well, I just butchered that. If I were to graph y is equal to 2 to the x, 2 to the x would be right here. We did that yesterday. 2 to the x does that. So you can see the symmetry with respect to the line y is equal to x. All right? All right. This is a shift of log base 2 of x. It's a shift. It's a shift left 4 and down 3. Left 4, down 3. So my vertical asymptote, which was on the y-axis, is shifting to the left 4. So my asymptote will be x is equal to negative 4. I'm going to go take care of that. Okay. And now I'm shifting it down 3. So my key point here was the point 1, 0. So if I'm shifting, it was 1, 0, and now I'm shifting it down 3. So it's negative 3, 0. Negative 3, negative 3. Okay. And then I would go up where I was at 2 over, I would go 1 up. If I go 4 over, I'll go 2 up. If I go 8 over, I'll go 3 up. Just like that. What will this do to the curve? Okay, how does this relate? Well, a negative will reflect our log curve over the x-axis. It'll reflect it over the x-axis. So our asymptote is still the y-axis. But now we're reflecting it over the x-axis. Our first point will still be the same. But this time, instead of going 2 over and 1 up, we'll go 2 over and 1 down. Instead of going 4 over and 2 up, we'll go 4 over and 2 down. 8 and 3. And then we can use those to sketch the graph. Okay. Alrighty. What about if your negative is in there with the x? If it's in there with the x, it's going to be a reflection again, but this time it's over the y-axis. Okay, I'm getting really messy with my handwriting. I've done too many videos today. Alrighty. The asymptote is still on the x-axis. I'm sorry, still on the y-axis. Instead of our action being over on the right side, though, now it's going to be reflecting it over the y-axis. So we're going to go over that 1, over 2 up 1, over 4 up 2, over 8 up 3. And then we sketch our curve. So these are log graphs. They have vertical axes of symmetry. Okay. The common log. The common log is a log with base 10. Okay. We don't write it using a base 10, though. It is conventional that we just don't put a base. We don't show a base at all. If you don't see a base, it means it's base 10. The common log. Common log is used in some areas of science, a few areas of science, like the pH scale, the Richter scale, and decibels. They all use base 10 logs. Okay? So if you don't see a base on a log, it is assumed to be a 10 in this course. I say in this course because later on, if you see a log with no base, it's assumed to be the natural log. And I know that's a little confusing, but not for this course. For this course, no base shown means it's the common log, log base 10. Okay, similar to how if you see this, your root is assumed to be an index of 2. Okay, whereas if it's another root, you have to show the number for it. Okay, the natural log. The natural log is a log with a base of e. Okay, we write it as ln of x. ln of x. The natural log has many, many uses. It is frequently found in nature. Therefore, we use it in a lot of science. Science uses the natural log. In calculus, we use the natural log almost exclusively. Just as you cannot do geometry and trig without pi, you can't do calculus and many of the sciences without e. Okay? So if it's called natural log, why do we say ln and not nl? A couple of different theories for that. One is that it comes from the Latin. I'm not going to try to pronounce that, but it comes from Latin where it's ln. Another theory is that Leonard Euler, who spoke French and used the natural log a lot, in French you would write it like that and pronounce it with an L before the N. And ln is based on e. It has base e. E is Euler's number. He created it. He found it. So it makes sense. If that is where we get ln from, it makes sense that we use what he used. Okay, just a word about terminology. The expression log base b of a is pronounced log base b of a, or you could say log of a base b. Okay, b is the base. The a is the argument of the log. You will hear me say, what is the argument? You'll hear me talk about the argument, okay, and the base. So you need to know when I say the argument, I mean this, whatever we're taking the log of. Okay? Properties of logs. Just as we have properties for exponents, we have properties for logs. Okay? And they vaguely relate to each other. They definitely relate to each other. I shouldn't say vaguely, they definitely relate to each other. Okay? Just as multiplication in exponentials somehow does something with addition, we do the same thing for logs. Log base b of n times m is log base b of n plus log base b of n. So you can think of this as I can split up my argument into two different logs with the same base. The two logs are added together. Okay? And just as in exponentials, when dividing two functions with the same base, two expressions with the same base, you subtract their powers. If you are dividing, if your argument is being divided, we can split this up into two logs with the same base. Whatever is on top gets a positive log. Whatever is on the bottom gets a negative log. Okay? For every log, for any base, if the argument is 1, the value is 0. If the argument is the same as the base, the value is 1. Log base 2 of 2 is 1. Log base 3 of 3 is 1. And now we have a property that is used a lot. We use this one a lot. We use all of these a lot. If your argument, and only your argument, has a power on it, we can move that power and make it the coefficient of the log. We can move it out to the front and make it the coefficient. This will be m log base b of n. And vice versa. You can move the coefficient back to the power on the argument if you want to. Lastly, we have what we call the change of base formula. The change of base allows us to change the base on the log to any other base we want. Okay? Any other base we want. Log base 2 of the argument divided by log base 2 of the old base. Log base 3 of the argument divided by log base 3 of the old base. Log base 10 of the argument divided by log base 10 of the old base. Or natural log of the argument divided by natural log of your old base. We can write any base we want this way, and we do. Okay, in calculus, this is our go-to. If we start with a different base, we go immediately to that base. Okay? On calculators, they have ln and they have common log. Those are the two on the calculator. So those are the two that we go to. If we're using our calculator and we have to punch it into our calculator, we use one of these. Doesn't matter which one. Okay, for instance, might as well do this. Let me see what's on here. Okay, if I wanted to put in, if I wanted a decimal for log base 2 of 7, if I wanted that, I would type in ln of 7 divided by ln of 2. But you could do log of 7 divided by log of 2. They are the same number. It doesn't matter what your base is. Okay. One thing to note about notation, if I see on your paper this, that means log base 2 of x all plus 3. You're adding 3 to log base 2 of x. If you want x plus 3 to be your argument, you must put it in parentheses like that. Okay? Alrighty. Let's do a few examples, how you might see some of these. You need to be able to manipulate logs randomly. in any way. You need to be able to manipulate them by hand, no calculator. So log of 1/5. What could we possibly do with that? Well, I take a look at some of my answer choices to guide me. Where do they want me to go with this? Well, one thing that I can do with this is I can write 1/5 as 5 to the negative 1, because 1/5 is 5 to the negative 1. Now I can use the property that allows us to bring any power on the argument to the coefficient of your log. So that will be a negative 1 log of 5. C. What about this one? What can we do with this one? Well, if I see two logs with the same base, I'm going to think about combining those and making them one log. Okay? So the 12 was with a positive log, so a single log would have that 12 in the numerator of its argument. The 48 is from a negative log, so the 48 will be in the denominator of the argument on the single log. So this is log of 12 over 48, which is 1 over 4. That's not one of my choices. I do know this cannot be my answer choice, though. So this is log of 4 to the negative first power, and then we can move our negative 1 to the coefficient of the log and make it negative log of 4. B. Okay, so I'm just manipulating. Manipulate until I get one of the answer choices. Okay, number 3. I notice that these are all single logs. All of them are single logs. So I know I'm going to be getting this together to be one single log. Now there are 5 logs, even though I see ln of 1, and that is 0. I can zero that out immediately. It's not going to affect anything here. I'm just subtracting 0. Okay, I'm going to write this as a single log. The 4 is with a negative log. So in a single log, that 4 will go into the denominator. The 32 is with a positive log, so the 32 goes in the numerator. The 16 is with a negative log, so the 16 goes in the denominator and gets multiplied by the 4 that was already there. The 8 is with a positive log, so it goes into the numerator and gets multiplied by the 32 that was already there. Okay, now I'm going to reduce. 4 goes into 32 8 times. 8 goes into 16 twice. 2 goes into 8 4 times. I've only got a 1 left on the bottom and a 4 left on top, so this is ln of 4. Is that one of my choices? It is not one of my choices. How can I get to one of my choices? Well, 4 is 2 squared. And now I can move this 2 to the coefficient of the log to match one of the choices. 2 natural log 2. Okay. In number 4, we start with a single log, and they write it all expanded. So let's write it as in expanded form. Well, the first thing I'm going to do before I do that, I see 2 over 10, and I am not going to write it as 2 over 10. I'm going to reduce that and make it a 5. Okay? So let's expand this. I'm going to start in the numerator. I'm going to give it a positive log, and this is the cube root of x minus 7, which I'm going to write as a power. What will the power be? The power will be 1/3. but I'm not going to put the power on the argument. Instead, I'm going to put the power in front of the log as a coefficient. That is completely expanded form, and I see that in two of my choices here. Okay, let's go now to the denominator. Let's handle this 5. There are going to be two parts to the denominator. Okay, ln of the 5, and I'll need an ln of this other piece. So I am going to write ln of 5, but the 5 is in the denominator, so it gets a negative log. Okay, now I'm going to go and write ln of the x plus 9. It has a 6 power. I'm bringing the 6 out to the coefficient of the log. This was in the denominator, so it gets a negative log. So that correct answer looks like B. Okay. Let's write this expression using a single log with one argument. Okay. That single log has to be ln because that's every log there. Okay. The first term is positive, so what I'm about to write is going to go into the numerator. I do see some negative logs, so I know I'm going to have a denominator. I'm going to write the first thing here. X is going to be x to the 3rd power. Here we have x plus 5 to the 4th power. It's in the denominator because we have a negative log. This has a power of 1/5. It's with a positive log, so the argument is that this piece will be in the numerator. And I could write it as a 1/5 power, or I could write it as a 5th root. Since they didn't give me multiple choice, it's my choice. I'm going to write it as a 5th root. Okay. Last piece, the x plus 7 has a power of 8. It has a negative with it, so it goes in the denominator with the x plus 5 to the 4th. So x plus 7 to the 8. And that is a single log with one argument. Okay, last example. Evaluate this expression if x is 8 and w is 3. Alrighty, so I'm going to put 8 in for x, 3 in for w, so I'm going to have 3 ln absolute value of 8 minus 5 is 3, 8 plus 1 is 9, minus 3 ln of 3 minus 7 is negative 4, 3 plus 1 is positive 4. Okay, so this is 3 ln of 1/3 minus 3 ln of the absolute value of negative 1 is 1. ln of 1 is 0. So this is just 3 ln of 1/3. And I look over here and that's not there. So what did they do? Well, quite likely they changed 1/3 to 3 to the negative 1. 3 to the negative 1. And then they pulled the exponent on the argument and made it the coefficient, part of the coefficient on the log. So negative 3 ln 3. And that is answer choice D. Okay, so logs I think are really fun. They're fun to manipulate. You might not think they're fun, but I think they are fun. Fun to manipulate. It's fun to try to get one of the choices in a multiple choice question, I think.